This is lecture 22, and in the last lecture we had looked at the mass conservation equation and the species conservation equation for a 1D planar premixed flame. We made a lot of assumptions. We said that it is constant area, steady flow, constant properties, Lewis number equal to 1, things like that, and we could do mass and species conservation equation in the last class. So, today we will have to look at the energy conservation equation for this 1D flame. It will take us quite a bit of time, but this is necessary. First we will get the energy equation for the 1D flame, then apply it for the particular flame propagation situation that we have. So, let us look at the situation like this, where there is a slice of thickness delta x in the domain. So, there is a slice of thickness delta x in the domain, and you will notice that there are 2 arrows going into the slice and 2 arrows going out of the slice. So, we have this term which is m dot a double prime into area into h plus v squared by 2 plus g z. This is at x, and we have a similar term here, which corresponds to the values at x plus delta x. I also have q dot x double prime a at x and also at x plus delta x, that is the other term. Now, what is q dot x a double prime? It is a heat flux term. Okay. So, we will have to look at that in more detail in a few minutes. So, apart from these 4 terms which we see, there is also a w dot c v term which has been shown with an arrow going out of the control volume. So, this is the work done by the control volume. Now, in this case there is no work that we are considering, there is no rotating shaft, no work that we are considering. So, there is no need of keeping this w dot c v. So, based on what you see, the 4 energy flow terms, this equation can be written. The equation which you see at the bottom of the screen, this equation can be written. So, this is quite straightforward. I have written w dot c v equal to 0.
Sir, what is the value of q?
Yes, yes. So, we will just come to that in 1 minute. Q dot x double prime is the heat flux, okay, and we will see that this has 2 contributions. We will see this very shortly. Now, the slice that you see, slice of thickness delta x, this is in the domain, and in the domain there are temperature variations, for example, because we have a flame, and since we have a flame, there is high temperature in the flame region, in the unburnt region there is low temperature. So, there is a variation of temperature with x. We are talking about only one spatial coordinate now, that is x. So, that delta x is some zone in x. Remember, again we are doing a 1D problem. So, the heat flux term is q dot x double prime. We are writing it with subscript x because the heat flux is actually in the x direction. Now, going a little further, now at the top of the screen you have that equation which we just now wrote, setting w dot c v equal to 0, and this equation here can be simplified to this. Now, how do we do that? Divide both sides by delta x and let delta x go towards 0, correct? This can be done. How do you know that this is what has been done? Because you now see derivatives. In this equation, in this line, you now see derivatives. They came because In the previous equation you had, for example, q dot x double prime minus q dot x plus delta x double prime. So, this is a change in q dot x between x and x plus delta x. So, if you divide that difference by delta x, let delta x tend towards 0, then you will get a derivative, and that is what has happened in this stage. You got a derivative. Now, coming to the question of q dot x double prime. So, q dot x double prime is minus k dt dx plus this summation term, which has a diffusive mass fluxes of individual species multiplied by h I. Okay. So, if you look at this, immediately you will recognize that this looks a little different. If q dot x double prime was minus k dt dx, then that would have been straightforward, because there is temperature gradient in the domain. So, there will be heat flux governed by Fourier's law. So, you could have written minus k dt dx for q dot x double prime. Why do we have additional terms? Because now we have multiple species. Remember, we are doing a combustion problem, so there are multiple species, and these species do not necessarily move with the same mass with the same velocity as the center of mass of the mixture. We discussed that some time back. We said that the individual species may have velocities which are different from the bulk velocity. Okay. And the difference is kind of a relative velocity, which leads to diffusional mass fluxes. Okay, so, this is familiar to us. Again, we had done this first time, I think, when we were doing the well stirred reactor. So, at that point of time, we wrote diffusive mass fluxes for the ith species. For the well stirred reactor, of course, remember that we said that the mixing is so good that we could neglect the diffusional fluxes, but in general we have to keep diffusional mass fluxes. Now, compared to the bulk flow, individual species have individual mass fluxes, diffusional mass fluxes. So, those diffusional mass fluxes are m dot I double prime comma diff, and if you multiply that by h I is the enthalpy carried by the ith species, and if you do a summation of this, this will contribute to the q dot x double prime. So, the heat flux is not just because of minus k dt dx, but because of this additional diffusional mass fluxes. These additional diffusional mass fluxes do not directly come through the m dot double prime term. See, we already wrote m dot double prime into h plus v squared by 2 into g z. That cannot take care of the m dot I diffusion double prime, that is the diffusional mass flux of the ith species. So, that is why we have to write it like this. Okay, and again, if you look at this, probably you will identify, you will probably know this. This is diffusional mass flux is equal to the ith species mass flux minus a contribution due to the bulk flow. Okay, or if it is easier for you to think the other way, think of moving this negative term to the other side. Then m dot I double prime is the diffusional mass flux plus the bulk mass flux into y I. Okay. So, this we had done.
Sir?
Yes.
Sir, in equation of qx,
Yeah.
h I is a function of t.
H I will be a function of t.
Function of t.
Yeah.
Then what is the value of t? That means t will be varying from, for instance, del x.
Yeah, t is a local t. The t that you see anywhere, for example, you see a t here also, this is a local t, local meaning at that particular value of x. So, this h, see the question that he is asking is h dependent on temperature? Of course, it is dependent on temperature, but then what is the temperature he is asking? That temperature is the temperature at that particular x. So, q dot x double prime is a heat flux value at a particular x. So, at that x there is a temperature. So, that temperature will determine what is the value of h I. So, Hi depends on the particular species that we are talking about, it also depends on the temperature locally. Okay, so this is actually our energy equation. We can see this. We can see this one. This is our energy equation, correct? But of course, this is not a satisfactory form. So, we have, because it just has q dot x double prime, we cannot directly deal with q dot x double prime. So, we want something for q dot x double prime. We have written that. So, we will do several stages of simplifying this, modifying the form to get an energy equation in a form which is useful to us. Okay. Again, what is the purpose of doing all this? Remember that Maillard and Le Chatelier had given a simple thermal theory for flame propagation, but there we got SL as a proportionality, SL proportional to square root of alpha into reaction rate. This is what we had done in the last class, lecture 21. Now, we are not happy with that, because we want an expression for SL, SL equal to something which will allow us to calculate SL and for various mixtures have some good estimates of what SL will be like. We are doing a simple theory. The expression that we will get will not be very sophisticated, but it will still be better than what Maillard and Le Chatelier had done more than 130 years back. Okay. So, this is what we have now for q dot x double prime. This is the energy equation that we have. Now, let us see whether we can proceed further on this. All right. This is a slight bit of manipulation. So, q dot x double prime is minus k dt dx plus the diffusion mass flux into Hi summation. That is what we had written. Now, we have changed this in terms of m dot I double prime and m dot double prime into Yi. Is that possible? So, we have written the diffusional mass flux as the species individual mass flux minus the bulk flow contribution. So, m dot double prime is one number. So, it can be moved out of the summation, and now we get summation Yi Hi, correct? So, please let me know whether this is okay. Now, summation Yi Hi is H. So, what is H? H is the enthalpy of the mixture on a per unit mass basis. So, this is now an expression for q dot x double prime. This equation number that you see, I think corresponds to second edition of Terns's book. I think the number is a little different than third edition. Going back to again our energy equation, this is the energy equation. We saw this in the last page. So, there is a V dV dx which has to do with kinetic energy, and then we of course have dH dx and we have d dx of q dot x double prime. So, we got this few minutes back, and this is now our expression for q dot x double prime. Again, this is a valid energy equation, but we are trying to write in a form which is more useful to us. So, let us look at the screen now and look at the first equation that we have, which is for q dot x double prime, and second equation is the energy equation basic form. Also have a look at the third equation. Do you think we can get the third equation from the second using the first line? Do you think it will come? The third equation is also energy equation. Third equation is also energy equation, but you will notice that this energy equation, that is the third equation, does not have a q dot x double prime, because it has been replaced. Because it has been replaced, and there is proof that it has been replaced, because we now got minus k dt dx in the equation, and we got this term which must have come from here. This term must have given this, correct? Has something disappeared?
M double prime dh by dx.
Yeah, so m dot double prime dh dx must have come from d dx of this, but there was already one m dot double prime dh dx, so those got cancelled. Yeah, so it is little tedious, but I think if you slowly look at all this, you should be able to see which terms have which terms are there and which terms have disappeared and why. So, this is now our energy equation. This looks little better because it does not have q dot x double prime. We do not want to deal with q dot x double prime, because it is better to deal with, let us say, temperature and enthalpy and things like that. Okay. We will do some more work on this. So, for that, I think let us concentrate on this term. Yes, so we will concentrate on this term. And please have a look at what I write here. So, that is straightforward. That is just differentiating term wise. So, we got two terms like this. Okay. And we do now a small trick to bring in the species conservation equation. So, what we have here is d dx of m dot I double prime, d dx of m dot I double prime, but d dx of m dot I double prime is m dot I triple prime. Okay. Is that correct? Where does it come from? This comes from,
It is the mass generation per
yeah. So, this equation is something which we derived in the last class by taking a slice and considering the species inflow and outflow and the species generation in that control volume. So, we call this a species conservation equation, isn't it? We call this a species conservation equation. So, this is the species conservation equation. So, that can be utilized here. So, if we do that, then we will get something like this. Okay, here you will see on the right hand side summation h I m dot I triple prime. Okay, so where does that come from? We used d dx of m dot I double prime equal to m dot I triple prime, species mass conservation, correct. So, what you see here is still energy equation, but in a different form. Now, this energy conservation equation has the species conservation equation built into it. Okay. Now, we will again go a little further and try to make further simplifications, and that is possible using what is known as a Schwab-Zeldovich form. So, this is SHVAB, the name of one researcher, Schwab, and Zeldovich, of course, you are familiar with, Russian scientist who gave us also this Zeldovich mechanism. So, a crux of the Schwab-Zeldovich form is to assume Lewis number equal to 1. Let us see how it works. Let us look at this now. This is q dot x double prime. The first line is q dot x double prime. We have done that some time back. I said that this is a combustion sort of situation. There are many species flowing, so there are diffusion mass fluxes of individual species. Individual species carry enthalpy. Each individual species carries enthalpy H I. Okay. So, up to this you had seen, and then now I go to the next one, the next line. What have I done now between the first and the second line? We have used Fick's law. Okay. So, the diffusional mass flux has been written as minus rho d, rho is the density of the mixture, into dyi dx. Okay. So, that is the first step, that is the second line. What have I done in the third line now? In the second line, we had summation h I dyi dx in the second term. Okay. Instead of that, now I am writing a difference of d dx of summation h I y I and summation y I d h I dx. Should I clarify this, or this is okay? It's okay. Huh? Essentially, what I am doing is summation y I h I. I am differentiating summation y I h I to get summation h I dy dx plus summation y I d h I dx. Fine. Let us also notice what we have here. Y I d h I dx is same as y I c p I d t dx, assuming that dh can be written as cp dt dx, dh can be written as cp dt. Okay. In any case, we are assuming ideal gases, and at the next step we write that equal to cp dt dx. How? Summation y I c p I must be cp of the mixture. Okay, summation y I C p I must be C p of the mixture. That is why this whole term summation y I d h I d x becomes C p d t d x. Okay. We are doing lots of manipulations. So, let us again not lose track of what we are doing. We have an energy equation which had a q dot x double prime. Now, in that q dot x double prime, we are now have a minus k dt dx term, and we have these two terms, and out of these two terms the second term can now be written as rho d C p dt dx. I mean the third term on the right hand side. Okay. This can be written as rho d C p dt dx now. Okay. This is how it should look like. First line, we had a minus k dt dx. The third term I told you should be rho d C p dt dx, correct? That's it. Okay. So, we had this equation, this energy equation minus k dt dx minus rho d d dx of summation h I y I plus rho d summation y I d h I dx. Okay. So, we were doing the Schwab-Zeldovich form, and just a few minutes back we saw that this last term should be rho d C p dt dx, because y I d h I dx could be written as y I C p I dt dx, and summation y I C p I is C p. So, this term became rho d C p dt dx, correct. We already had this minus k dt dx term, and this term can be written as minus rho d. See, summation y I h I is h. So, that is d h dx. So, we have this. Now, we also made one assumption when discussing the problem. We are discussing this 1D premixed laminar flame propagation. We said that we will take Lewis number is equal to 1. Lewis number is alpha divided by d. You may have seen this when you have done a convective heat and mass transfer course. So, this is alpha by d, that is thermal diffusivity divided by mass diffusivity. Now, what is thermal diffusivity? Thermal diffusivity is k by rho C p, everybody knows that, and the mass diffusivity we are just characterizing with one mass diffusivity d. Okay. So, that is k by rho C p d equal to 1, which means k equal to rho C p d, and that tells you that this is also equal to k, isn't it, this term, because this term is rho d C p and d equal to alpha. So, it is rho alpha C p, which is k, right. So, that means it will just make our job easier, and we should be able to cancel these two terms.
So, this assumption means
How good is the assumption?
how
Yeah. So, his question is how good is the assumption? Why are we saying Lewis number is equal to 1? Now, it is not perfect, but remember that we are doing a simplified theory. We are trying to do the theory which is easier for us to do, that is all, because otherwise there will be too many complications to handle. Now, is that still can this be justified to some extent? Yes, because Lewis number in typical combustion situations are of the order of 1. By of the order of 1 I mean maybe 0.7, maybe 1.2, things like that, but not very far away from 1. So, if you take a realistic mixture, calculate alpha d and then take the ratio alpha by d to calculate the Lewis number, it is of the order of 1. So, we are not very far off from 1. It is not equal to 1 definitely. You have to be extremely lucky to get a Lewis number equal to 1, but it is of the order of 1, and in many theoretical analysis of combustion you assume Lewis number to be equal to 1 for the sake of simplicity. It so happens that taking Lewis number equal to 1 will still give us something reasonable. So, the advantage that we now see is that q dot x double prime has become equal to minus rho d dh dx. So, it has become a simpler equation, and our energy conservation equation is based on what we just now have. So, where do we get this from? This has come from that q dot x double prime. Q dot x double prime, the last thing that we got was minus rho d dh dx, correct, after Lewis number equal to 1 assumption. So, this left hand side is what? What is the left hand side? It is minus d dx of q dot x double prime, the left hand side, and the right hand side we already had in this form quite some time back. Quite some time back we had this form. Just in case you are having difficulty connecting to what I am saying, I will write this in brackets. We had this, correct. So, q dot x double prime has been written as minus rho d dh dx after assuming Lewis number equal to 1. So, this is now our energy equation. And ultimately actually our job is still not done, we will still like to go little further with this, and let us think about what is H. H is of course summation y I h f I naught when I write H, it means the mixture. We are talking about the mixture when you write H. So, that must be summation y I h I, where h I is for individual species, it is equal to the enthalpy of formation plus integral C p I dt. Okay. So, once we have done that, remembering that all C p's are the same, we should be able to get this. Okay. So, there is no C p I here because summation y I C p I is C p. So, from that we have been able to get this. So, that is H. and this is our energy equation, this is H. So, if you put the two together, then we get something like this. So, this was the energy equation. Just few minutes back, this was the energy equation, correct? This thing that has this H. Now, H has been replaced. H has been replaced in terms of this enthalpy of formation and integral Cp dt. That is why we have got all this. Again, if it is not immediately clear to you, I think that is not a problem. It is actually not complicated, just substitution. So, we can write again just slight bit of reorganizing. Now, what I have here is this term this sort of thing here after reorganizing. And this can be written as m dot I double prime. Is that okay? Because this is the bulk flow contribution and this is the diffusion mass flux. So, they will together give you m dot I double prime. M dot I double prime is the mass flux, the absolute mass flux of the ith species. Okay. We will do one more thing, we will say that the changes in kinetic energy are negligible. So, we will get rid of this. We could have done that previously also, but let us do it now. This term m dot double prime v dv dx is small compared to the other terms, actually small compared to the other terms which you see in this equation. The kinetic change in kinetic energy term is neglected. And let us notice one more thing, that this is d dx of summation h f I m dot I double prime. So, you can do a d dx of d dx here. If you bring the d dx here, then it will become d dx of m dot I double prime, which is the same as m dot I triple prime, which is on the basis of the species conservation equation. So, we are neglecting the kinetic energy changes in kinetic energy term, and we will bring the d dx here to get d dx of m dot I double prime, that will give us m dot I triple prime. Okay. So, as a next step, we will get m dot double prime we will get this. So, the last term, that is the only term which you see on the right hand side, has m dot I triple prime. So, that means that must have come from d dx of m dot I double prime. Okay. Must have come from d dx of m dot I double prime. So, this is our energy equation, and it is possible to work with this energy equation. In fact, it will become even simpler for us, because we can take this C p to be constant. C p is not changing according to the assumptions that we made for our flame. Okay. So, even C p can be taken out, so that this equation can become m dot double prime into C p dt dx, plus here also the C p can be taken out. We can do things like that. C p can come out of the differentiation here. Okay. Now, based on all that above, we can write for our flame, our 1D situation, 1D flame, we can write m dot double prime C p dt dx minus d dx of
You also assume rho d and Cp to be constant, so we can take that.
rho d C p can be also taken out. So, this is one form, but you can of course rho d C p is also equal to k, and then k is constant. So, that can be done. So, this is a convenient form of the energy equation, and as we were saying, this is definitely also equal to k. So, you can look at this term and you can see that okay, there is a transfer of enthalpy because of the mass flux, which is m dot double prime. So, this bulk flow m dot double prime gives you an energy transport. There is also energy transport because of heat conduction. So, this is d dx of k dt dx, and these two are balancing the thermal energy release because of chemical reaction. So, this is an energy equation for a reacting flow situation, correct? And if you look at this, the last term will tell you that chemical reaction is happening, because the last term has m dot I triple prime, which is the production rate of the ith species. What is the unit of m dot I triple prime again? It is per unit time per unit volume. So, the ith mass production rate of the ith species per unit time per unit volume is what we are calling m dot I triple prime. Where will this come from? This will come from chemical kinetics. Chemical kinetics tells us about rates of reactions. So, we have been doing chemical kinetics for quite some time, and we know that okay, there are expressions for, let us say, dA dt, dB dt, concentration of A, concentration of B, etc. We were doing this for a general bimolecular reaction like A plus B giving you C plus D, and we learned how to write dA dt in terms of various things like a pre-exponential factor, concentrations, then temperatures. We learned all of that. We also learned that it can be very complex because there can be multiple step reactions. We are not talking about one single reaction, or it can be made simpler, forcefully made simpler if we assume a single step reaction. In fact, remember the discussion that we had in the last class? We will model this chemical reaction in this case. We are talking about a hydrocarbon combustion reaction, okay, gaseous hydrocarbon burning in air. That is why you have this premix flame propagation, right. So, in that case, we can assume the simplest possible model. In the last class, I told you that the model that we will assume is a single step irreversible exothermic reaction. So, there is some model. So, we will have to look at that in more detail, but that will connect to the m dot I triple prime term. So, the chemistry part comes from this. What does this term tell you? It tells you that the ith species is getting produced at a certain rate, and that is associated with its enthalpy of formation, and together they give you an energy term because of chemical reaction. It has contributions from all species which are there in the mixture. What is the minimum number of species that we can deal with in the simplest possible case? We said 3. We said 3. So, here these 3 terms will be for fuel, for oxidizer, and for products. So, we just have enough time to concentrate on the right hand side. So, I will just write this one, RHS of this energy equation that we had.
Sir,
yeah.
This form that we derived, this is the Schwab-Zeldovich form.
This is the last equation that we had. Yeah, this is the Schwab-Zeldovich form, because the heat flux term became simpler. The heat flux term actually had 3 terms, and then it got simplified, and then we got for q dot x double prime we just got minus rho d dh dx. It became q dot x double prime became minus rho d dh dx. That is after the Schwab-Zeldovich approximation, where we took Lewis number equal to 1. So, that is how it became easier. Okay.
And it also seems that just before starting the Schwab-Zeldovich form, we got one form of the energy equation. It seems that from there also just 2-3 lines of simplification will give the same result as we did.
No, but we have been able to get rid of some terms because we assumed Lewis number equal to 1. Okay. I just write maybe one line. This was on the computer, so I will have to write this again. Q dot x double prime is minus k dt dx minus rho d dh dx plus rho d cp dt dx. We had this, and we took alpha by d equal to 1, and then q dot x double prime became this. Okay. So, this is the simplification which we have used to get to this form which we have now. What is the form that we have now? We have this form. This is the form that we are going to work with. Okay. You can keep in mind, as you pointed out, that rho d Cp is also equal to k. Okay. So, this is the form after doing everything. This is what we are going to work with. So, coming back to the right hand side, we are talking about this right hand side. So, the right hand side is this, which we write as enthalpy of formation of the fuel into m dot triple prime for the fuel, and similar terms for the oxidizer and the products, which is yeah. This is products, yeah. So, what have I done? The first line is easy from here. First line is just, instead of writing the summation sign, writing out individual terms. That is the first line, this line, second line rather. And in the third line, what have I done? I have replaced m dot triple prime oxidizer and m dot triple prime product in terms of m dot f triple prime. So, that we are done in the last class, correct? Okay. So, now it becomes minus m dot f triple prime and this is nothing but heat of combustion. To the right hand side is the rate of production of fuel into delta H c with a minus sign. We are running out of time, so I do not have sufficient time to explain this now, but we will do that in the next class. This is delta H c. Okay. So, this is our energy equation. Our energy equation is now pretty much ready, but we will have to see how to apply this to get laminar burning velocity. We are trying to do a 1D premix stream analysis, where our purpose is to get an expression, an equality for laminar burning velocity. For that, we have done preparation for two classes. In the last class, we had got the mass conservation equation and the species conservation equation. Today, we had the most difficult task, in the sense that it took us a lot of time to actually get just the energy equation for the 1D case. But now we still have to see how to apply these equations and get laminar burning velocity. So, we will do that in tomorrow's class.